All right, guys, welcome back. This is going to be the 8.7 instructional video, part one. We're not going to cover everything here. And what we are going to kick off 8.7 with is a question. Okay, and maybe you've seen a type of this question before. There's a lot of different variations out there. They don't all have the same answer, but they all get at the same idea. And what this is infamously known as is the penny problem or the lottery problem, depending on how you look at it. So what I would like you to do, pause the video and see if you can solve this on your own. See if you would rather, or make the decision about whether you'd rather get $1 million and then receive 100,000 a day for 30 days, or receive a penny at the beginning, but then every day your money total would be doubled. So pause the video, see if you can figure it out. Well, as we work through this problem, let's really take a closer look at what is happening here. Let's look at the first option. What does the first option say? It says you would get $1 million and then receive 100,000 a day for 30 days. So maybe draw a little chart, right? See what's happening here. Draw a little chart and let's really look at what's happening here, right? I'm receiving $1 million. Okay, so I have that off the bat. And then I'm getting $100,000 a day for 30 days. So I start with $1 million, and then on day one, I get an additional 100,000. On day two, I get 100,000 more. Day three, 100,000 more. Okay, and so maybe it'd be a little better if we wrote our totals here, right? That's the amount I'm getting every day. So on day one, after day one, I now have $1,100,000. After day two, I now have $1,200,000. Day three, at the end of it, I'm going to have $1,300,000, and so on and so forth. Okay, and again, this comes from the idea you get $1 million and then you get 100,000 a day for 30 days. And really what you can do is you can break this into two parts. You have your initial amount and then you simply get 100,000 a day for 30 days. Now, instead of adding 100,000 30 times in a calculator, we all understand that repeated addition is the same thing as multiplication. And so really the best way we could summarize option number one is saying I have $1 million plus 30 times 100,000, because for 30 days I'm going to get $100,000. And by doing this little problem, you end up with a grand total of $4 million. Okay? 1 million from the get-go, from the beginning, and then you get 3 million more by getting $100,000 a day for 30 days. Okay, so that's option number one, right? Option number one gets us $4 million. And I think you can all figure that out, but maybe the second one gave you a little bit more trouble. You see, the second one, we start and we get a penny, and then your money total gets doubled every day for 30 days. So if I want a game show, the host would hand me a penny and then say, okay, starting tomorrow, that money amount is going to get doubled every single day. So we start with 1 penny, okay? And then for 30 days, your money total gets doubled, okay? So at the end of day one, my money total gets doubled. So I now have, instead of 1 penny, 2 pennies. At the end of day two, I would have 4 pennies. At the end of day three, 8 pennies. At the end of day four, 16 cents or 16 pennies, okay? And you get the idea here, right? I start with 1 penny, and then my money total gets doubled every day for 30 days, okay? And maybe you sat there and you said, okay, what's happening, and you said, well, wait a minute, a different way of thinking about this, instead of writing out that whole chart, is, Mr. Carter, all that's happening is you start with 1 cent, and then at the end of day 1, you're going to multiply your total by 2, because that's what doubling means. And then at the end of day 2, you're going to multiply your total by 2. And at the end of day 3 and day 4, and you essentially multiply by 2 based on how many days there are, right? We start with 1 cent, and then every day for 30 days, my money total is doubled. But instead of typing a bunch of 2's in your calculator, just like we know repeated addition is multiplication, we know the shorthand way in math of writing repeated multiplication is with exponents. So what's really happening here? Well, I'm going to multiply my money total by 2 30 times, right? I'm going to have 32's multiplied together. Why? Because for 30 days, your money total gets doubled. Okay, so you multiply by 2 30 times, 2 to the 30th power. But remember, all these 2's were multiplied by your starting amount of 1 cent. So really, the easiest way to summarize what's happening with the penny is 0.01 times 2 to the 30th power. 0.01 times 2 to the 30th power. We start with 1 cent, and we will multiply that 1 cent by 2 30 times, because our money total gets doubled once a day for 30 days. So when we do that calculation, we end up with $10,737,418.24. Okay? And so clearly the better option is to go with the penny a day. Okay? Now, there are a bunch of different applications here, right? You could dig into and go, okay, well, when did the penny start to make sense? And you'll actually quickly find out the penny doesn't make sense till the very end, right? At the end of day 4, with the penny option, you only have 16 cents. Whereas at the end of day 4, with the $100,000 a day, you're going to have $1.4 million, or $1,400,000. And so while this starts off with very little amounts of money, by the end, if you keep doubling, right, your money amount's going to increase astronomically. If we went for one more day, my $10 million would turn into $20 million. If I want one day after that, it would turn into $40 million, right? Whereas again, we're only increasing by 100,000, okay? What this concept illustrates, among many concepts, is the idea of exponential growth, okay? And what we are going to do now in 8.7 is we are going to explore exponential functions, okay? And what are exponential functions? Well, unlike pretty much everything we've talked about so far, any equation or anything we've looked at to this point leading up to chapter 8 has been a line. We looked at all different types of lines, equations for lines, different things like that. But unfortunately, not everything in life is modeled by a line, right? While the example above, where we start with 1 million and get 100,000 every day consistently, would be modeled by a line, you can see that when you are doubling or tripling, right, instead of increasing by a set number, you are increasing by multiplication, then a line is not going to be an accurate model because you're not increasing by a consistent rate. Another good visual of this is driving, right? Maybe I'm driving a vehicle and I have a graph modeling my distance and my time, okay? Well, if I'm on cruise control, my graph may look like this, right? My distance is increasing. My distance is increasing as my time goes at a consistent rate, okay? While this would be a good model for being on cruise control, what happens when I enter the highway? Well, initially, I'm not covering very much distance as time goes on, but as I enter the highway, that rapidly changes, right? I begin to go faster and faster and faster. I'm covering more distance in less amounts of time. That's not accurately modeled by a line. rather by this curve. And so you can see in math, lines don't explain everything we see in the world. So we need things like exponential functions to model certain situations, okay? So let's dig into an exponential function. Just like slope-intercept form, the general form was y equals mx plus b. The general form for an exponential function is y equals a times b to the x, okay? All exponential functions are in some form or shape of this general function. Now, there might be a little bit more going on the parentheses than just a single number like we saw above, right? Above, we had 0.01 times 2 to the 30th, right? You might have a little bit more than a 2 going on there. We'll explore that in 8.8. But broadly, they're all exponential functions are going to be in this form. So let's break down each part. Well, if we look at our example from the penny problem, I think it'll be helpful for us to see what each part represents. Number one, y is going to be your total, okay? Y is going to stand for your total. In the penny problem above, this was the roughly, I'll put the about symbol here. This was about $10 million, okay? This was about $10 million, okay? Y is going to represent your total. A is going to represent your starting amount, okay? A will be your starting amount. This was the 1 cent in the penny problem, right? You have given 1 cent, okay? You are given 1 cent. Your rate of change is what's in parentheses. That will be your B, so to speak. B stands for your rate of change, okay? Your money is doubling, or your speed quadrupled, or hey, you had to slam on the brakes, so cut in half, right? Different things like that, okay? Bottom line, B is going to be your rate of change, okay? Finally, you are going to have your X value, and X is the number of times your rate occurs, okay? Many people mistakenly just put their time value up there for X. We don't want to do that because X is not just time, but rather it's the number of times your rate of change occurs, right? How many times am I doubling my money? Well, I'm doubling my money once a day for 30 days, so it will be doubled 30 times, okay? So practically, while that's an introduction to what exponential functions look like, what types of problems do we need to be doing? What types of problems, what's our goal here? Well, one of the things we want to do is we want to be able to evaluate exponential functions. And so we're going to evaluate the exponential function 4 times 3 to the x, okay? We're going to evaluate this, and we're going to evaluate it when x equals -3 and when x equals 6. So we got a couple different x values. We want to evaluate the exponential function. Well, evaluating isn't too complicated. You simply are going to plug in for x the various values you are given. So I'm going to plug in -3 for x. And in the past, you wouldn't have known what to do with this negative exponent. But because of your knowledge from 8.1 through 8.5, you know how to work with negative exponents. So how am I going to evaluate this? Well, the first thing I'm going to do is I'm going to simplify the negative exponent by rewriting it in the denominator. By rewriting it in the denominator of the fraction, it makes the negative exponent positive. And then I can solve from there, right? I know that 3 to the third is 3 3's multiplied together. 3 times 3 is 9. 9 times 3 is 27. And so what I figure out for my exponential function is that when x is -3, y is equal to 4/27. Do the same thing for when x equals 6. Again, please make sure you follow your order of operations here. Do not mistakenly do 4 times 3 and get 12. We must handle our exponents before multiplication. So the first thing I'll do is 3 to the 6th power, which I do not know off the top of my head. 3 to the 6th turns out to be 729, which we then multiply by 4, and we get 2,916. And so one of the things we want to be able to do with exponential functions is evaluate them for various x values given some a and b values. So let's take it a step further and apply it to a problem. Suppose 20 rabbits are taken to an island for an experiment. Biologists want to study how the rabbit population will grow if left to their own devices. The rabbit population triples every half year. The function y equals 20 times 3 to the x, where x is the number of half-year periods, models this situation. How many rabbits would there be after 2 years? Okay, so what we do is we are given an exponential function that models a rabbit population. What this means is y is going to represent your rabbit population. You can see the 20 is in that A spot when it comes to exponential functions, and that should make sense because we start with 20 rabbits. It should also make sense that 3 is in the parentheses for our B value. This is our rate of change, right? The rabbits are tripling every half year. And so the value we need to fill in order to solve this is they want to know how many rabbits there would be after 2 years. So how many rabbits tells me that we want to find y, our total population of rabbits, after 2 years. Now the temptation is just put 2 in for the exponent, but that's not correct. Remember, x is the number of times your rate of change occurs. So when we're looking at this, if x is the number of half-year periods, and we want to know how many rabbits there will be after 2 years, how many times did that rate of change happen? Well, if we're tripling every half year, and we do that for 2 years, there will be 4 times that we triple, right? At the 6-month mark, the year mark, the year and 6-month mark, and the 2-year mark, okay? Make sure you understand that x is the number of times the rate of change occurs, not just the physical time value, okay? So when we solve this, we do 3 to the 4th and we get 81. 81 times 20 and we get 1,620 rabbits, okay? That's how many rabbits there would be if the rabbit population tripled every half year for 2 years. And we started with 20. Working through another example, 10 animals are taken to an island and then the amount of animals quadruples every year. Write an equation to model the situation described above, and then we want to know how many animals there will be after 6 years. We're just writing an equation to model the situation. This is going to be an exponential equation, so we want to use the form a times b to the x. How do I know that? Because the population isn't increasing by a consistent amount, right? It's not like they're adding 40 animals every single year, right? The amount is quadrupling, okay? So the amount, if you're constantly quadrupling, the amount you change by in the first year will not be the same as the second or the third or the fourth, right? It's going to drastically increase, okay? Meaning our graph will look like a curve, and this is an exponential function. So at my general form, what is my a value? Well, that's how many animals I start with, which is 10. Quadruple implies the rate of change is 4. Okay, the rate of change is 4. We're quadrupling every year. And x will be the amount of times this rate of change occurs. So there's your general exponential function. They also want to know specifically how many animals are there after 6 years. Well, you started with 10, you're quadrupling. Now we got to ask how many times did we quadruple in that 6-year time frame? Well, it's quadrupling every year. So once a year, pretty much every year, you're quadrupling. There are 6 years, so your rate of change will happen 6 times, right? They quadruple every year, 6 years go by, 6 will be the number of times the quadrupling occurs. Number of times the quadrupling occurs. And when you plug this in to your calculator or solve it, you'll do 4 to the 6th, and whatever you get there, multiply it by 10. You are going to get 40,960 animals. Okay? So far what we've done, what we've learned how to do, we have learned how to evaluate exponential functions. We've learned the general form of exponential functions, and we have learned how to set up the general form of exponential functions given a real-world scenario. The last thing we're going to be discussing, and this will carry over into part 2, is we are going to talk about graphing exponential functions. Okay? And what we're going to do to graph these is we're going to treat them just like you initially learned how to graph with lines. Before you learned what slope, intercept, and standard and all of that good stuff was, when you just were given a line and you were first learning how to graph it, to get the general idea of what a line looked like, you probably took some x values, plugged them into your equation, found the y value, and then you saw what kind of picture it made. And when you had something like y equals 3x plus 7, when you plugged in those various x values and got the matching y values, and you graphed it, you saw your graph turned into a line. Okay? We already saw a preview up above with the car example with your distance when you're stepping on the accelerator, when you're merging onto the highway and you're picking up speed, your distance increases faster and faster and faster over smaller periods of time. Okay? What that showed us in a graph form was a curve. So we're expecting some sort of curve here. Well, let's go ahead and practice graphing exponential functions. So let's go ahead and graph the function y equals 3 times 2 to the x. And what we're going to do here is 4 steps. First things first, we're going to identify some x values. And I think the best way to do this is to pick 5 very specific x values. Though you could pick any 5 x values, I think the best ones to pick would be -2, -1, 0, 1, and 2. Now, why am I picking these? Well, one, since we're graphing by hand, they're going to produce relatively small numbers, right? If I picked 14 and I plug that in for x, I'm going to have to do 2 to the 14th power, and that's going to be massive. It's not going to fit well on my graph. 2, I picked some negative and some positive and 0 to see what the function looks like as it goes across the axis. Okay, so some relatively simple numbers, but ones that are going to give me a good depiction. Now, obviously, the more points you use, the more accurate your graph will be. 5 is a good number to use. It'll give us a general idea without taking too much time. So now that we have some x values we want to plug in, we need to, in order to graph these, find the appropriate y value. And we find the appropriate y value by plugging your various x values into the function. So we're going to go ahead and plug our various x values in. We're going to see what we get. So first things first, I need to plug in -2 for x. And when I do that, again, this is why we learned our exponent rules. What do I do in this scenario? Well, I know with negative exponents, I rewrite them on the opposite side of the fraction as positive exponents. Again, if you want to learn more about that idea and why I can just flip the side of the fraction, watch the 8.1 video. When I do this, the negative exponent becomes positive, and I end up with 3 over 4, which is 0.75. Now we'll plug in -1 for x, and it's going to look pretty similar. Again, flip the side of the fraction your negative exponent is on, and you can rewrite it as positive. And this leads me to 3 over 2, since 2 to the 1 is 2. And we know that is 1.5 as a decimal. I'm writing the table value as decimals just because they're a little easier to plot on the graph. Again, exponent rules, 2 to the 0 power, anything to the 0 power except for 0 to the 0 is 1. And 3 times 1 leaves me with 3. Plug in our next x value, 3 times 2 to the first power. 2 to the first power is 2. 3 times 2 is 6. And 3 times 2 to the second power. 2 to the second is 4. 3 times 4 is 12. And so what I've done is I picked some x values and I found their matching y values by plugging them, the x values, into the equation and seeing what the y turned out to be. Now finally, now that we have a table of values that we know make the equation true, right? These ordered pairs, negative 2.75, negative 1, 1.5, those combinations here, they will, when plugged into the equation, make the equation true. And so we will plot them on our graph. By the way, before we do, an interesting point to note, you will know you filled your table out correctly if in moving through your table, your rate of change is displayed. What do I mean by that? Well, what we're saying here with 2 to the x is we're saying we're doubling. Our rate of change is 2. We are doubling, okay? Well, if we are doubling, then we should expect that as our x value increases, we would multiply by 2. And that's exactly what happens. As my x value increases by 1, I multiply by 2. If this is not present in your table, you probably messed something up somewhere. You can see 3 to 6, multiply by 2. 6 to 12, multiply by 2. Okay, so just something to check yourself as you're making these tables. But let's plot our points. Negative 2 is at 0.75. Negative 1 is at 1.5. 0 is at 3. 1 is at 6. And 2 is at 12, so all the way up here. And what it looks like is, if I fill in, what we really kind of see here is we get this curve shape like we predicted earlier, okay? As our x value increases, so does our y value, but not at a consistent rate like a line, where every time you're going up 2 over 1, up 2 over 1, up 2 over 1. No, as your x value gets bigger, your y values get drastically bigger. And then this, again, goes back to the idea that they are doubling, okay? On the other end of the spectrum, you'll notice that we are still increasing, but it's at a not as steep rate as we move to the left. And you'll also notice that we never cross the x-axis. And you might be curious. You might go, wait a minute, Mr. Carter, why does the graph not go like that, like the dotted line? Well, let's again think about what's happening. We never plugged in one of these values, but let's pick a value way down here like negative 10. When we pick an x value like negative 10 and we plug it into our equation, what we're going to end up with is 3 over 2 to the 10th after we simplify using our understanding of negative exponents. Well, we don't know what 2 to the 10th is off the top of our head, but it's a really, really big number. It's a huge number. 3 divided by a big number is going to be a really small decimal that's close to 0, which is why this red line looks like it's getting closer and closer to 0, but doesn't get there, right? If I plugged in negative 100 for x, that would be 3 over 2 to the 100, okay? Again, you're going to get an incredibly small decimal that's really close to 0, but isn't quite there. That's why this red line goes down, but it never crosses the axis because of our idea of negative exponents. Guys, thank you for watching part 1. Hopefully this makes sense. Again, what you should be walking away with is the general form of an exponential function. How do we evaluate exponential functions when given specific x values? How do we create exponential functions in real-world scenarios? And finally, how do we graph exponential functions? Okay? We will dive more into the graphing piece in part 2, so stay tuned for that. Thanks for watching.